Hello and welcome to our presentation for the BMIP 2514 CAD CAM course. Today, my teammates Muhammad Afif Danial, Muhammad Akmal and I, Muhammad Yusuf Hamdani, will be presenting our end-to-end CAD CAM product development project. We will walk you through the complete digital design, machining and simulation of our chosen product, the multi-spanner. Let us start with the problem we aim to solve. In space-constrained mechanical environment, swapping out individual fixed wrenches is highly inefficient and often impractical. Our solution is precision-engineered multi-spanner. By integrating multiple hexagonal socket sizes into a single compact design, this tool significantly reduces toolbox clutter and enables rapid, on-the-spot adjustment. The core objective of this project was bridging the gap between digital geometry and tangible production. We accomplished this by first creating precise CAD models using parametric design and geometric constraint. Then, we defined specific machining operations, optimized our cutting parameters for efficiency, and finally generated the NCG code for CNC machine execution. I will now pass the presentation over to Afif to explain our methodology.
Thank you, Yusuf. To ensure absolute accuracy, we utilize a highly structured 4-phase CAM pipeline. As shown on this flowchart, our methodology progressed sequentially through Phase 1, initialization for brainstorming and research, Phase 2, digital development for CATIA modeling and assembly, Phase 3, simulation for toolpaths prove-out, and finally Phase 4, completion, where we post-process our work into NC code. Phase 1, initialization and material specification. During Phase 1, our conceptual research focused on identifying complex geometric features that requires advanced CNC machining strategies. We defined the physical limits and strict tolerances to guarantee structural integrity. Moving into digital development, we maintain data integrity via a strict 4-file architecture. This ensures our original 3D design remain uncorrupted throughout the manufacturing preparation. We utilize a part file for the primary solid model, an axis system file for the physical origin, an assembly file to integrate the two, and a machining file to configure tools and generate toolpath. This assembly-centric approach is critical for establishing the machining reference frame. As illustrated here, it digitally aligns the spanner exactly where the raw stock will be clamped physically. This effectively establishes the absolute reference frame for the CNC machine table without altering the original part geometry. Working strictly with CATIA's advanced machining workspace, we configured our advanced toolpath. Specific tools dictated our entire CAM strategy, allowing us to generate precise cutting coordinates mathematically for our progressive roughing and finishing operations. I will now hand it over to Akmal to discuss the simulation results.
Thank you, Afif. Our virtual profile demonstrated flawless tool movement. The digital simulation was highly successful and completed without software errors. Through real-time animation, we confirmed that smooth, dynamic tool movement achieved accurate milling for both the outer tool shape and the internal hex profile. We also verified the machining tolerance against our digital twin. Using a color-coded surface analysis, we mapped the remaining material to check the potential gouges. This direct verification step guarantees that our physical measurement will perfectly match the original CAD model. Preparing for actual production means anticipating real-world CNC machining variances. We mitigated tool deflection by programming extremely shallow gradual cuts. We also rigidly set safe retract heights to prevent clearance issue and ensure the cutter lives entirely clear of the stock to guarantee collision avoidance during rapid transit commands. For the final step, our toolpath was successfully post-processed into functional, machine-ready G-code All coordinates in the code are strictly bound to the machining reference axis, and we manually verify the speeds and fits for aluminum to maximize both tool life and finish quality. In conclusion, our transition from digital assembly to manufacturing read lines was a complete success. We executed this end-to-end CAD or CAM workflow without error, full achieving all technical requirements from 3D modeling to NC code generation. Our machining strategy is sound and generated code is prepared for real-world CNC milling. Thank you for your time and attention.